Hey everybody, we're back with the related rates part 2. If you flip into your packet to example 2, that is the example we're going to do in this video. So I'm going to start by reading it. A small balloon is released at a point 150 feet away from an observer who is on level ground. If the balloon goes straight up at a rate of 8 feet per second, how fast is the distance from the observer to the balloon changing when the balloon is 50 feet high? Okay, so let's start with a diagram. This is going to be pretty similar. As I'm reading this, I'm getting a familiar sense between this problem and example 1 because I'm already thinking of a right triangle. And when we did the ladder problem, we definitely had a right triangle. So what comes to mind is I've got to draw the observer. So here's going to be my observer who's on ground. So here, this will be my ground. And 150 feet away from the observer, and again, I'm going to put 150 feet on there because it's fixed, is the balloon. So here comes my artistic ability here. Here's my balloon. And the balloon is going to go straight up into the air. And what I'm tracking here is the distance between me and the balloon. And this will always be changing, but for now, I can just kind of model it like this. Now, two things are going to be changing at the same time. Obviously, the balloon, as it goes up, this distance will be changing, so I'll go ahead and call that an X. And as this changes, so will the distance between me, the observer, and the balloon. So this is Y. Okay. Now, givens. Let's start reading through this again. A small balloon is released at a point 150 feet away. I've got that. Second sentence. If the balloon goes straight up at a, here that word is, rate of 8 feet per second. So something equals 8 feet per second. But it needs a label. So let's think about this. This right here is changing at a rate of 8 feet per second. Well, that's X. So the change in X with respect to time is 8 feet per second. Comma, how fast is the distance from the observer to the balloon changing? Okay, how fast is this changing is what I seek to find. So how quickly is Y changing? I don't know, but I do know it will also be measured in feet per second. When the balloon is 50 feet in the air. So we want this calculation when X is 50 feet. So the 50 feet is really one of my givens, and what I'm trying to find is how quickly this distance is changing when we are 50 feet up in the air. Okay, so now I need an equation. I need an equation that's going to relate this diagram with X's and Y's, and again, I'm thinking Pythagorean theorem, just like the ladder problem. It'll be slightly different, though, because now my hypotenuse is a variable, so be careful of that. This is going to read x squared plus 150 squared equals y squared, or x squared plus, let me see what 150 squared is, 22,500 equals y squared. Okay, now I've got to bring in the element of time because my givens and what I'm trying to find involve it. So I'm going to implicitly differentiate this equation with respect to time. So let me click and drag this equation over. I've got x squared plus 22,500 equals y squared. So we're going to shortcut this. On the first video with example 1, I went through the y's of the implicit differentiation. Now we're just going to advance here and just go right to it. So here we go. The derivative of x squared, well, we know that's 2x. But we're implicitly differentiating with respect to time, so we have to tack on dx dt. Whatever variable that is, d that dt. Plus, with a constant, we can just go straight to 0. And finally, the derivative of y squared is 2y, but we'll tack on dy dt. Okay, so now what I have is 2x dx dt equals 2y dy dt. Not so bad. Okay, now it's time to fill in and solve. So anything here that we can fill in from up here is what we're going to do. So let's just start with the 2, then we move to the x. Do we know x? Yes, we do. X is 50. So 2 times 50 times dx dt, do we know that? Yep, it's 8 from up here, equals 2y. Do we have a y? We do not have a y, and we do not certainly have a dy dt, because I know that's what I'm trying to find. So pause there for side work. If I quickly redraw my situation here, my triangle's looking like this. Okay, I know this is 150, and I'm looking for dy dt at the moment x is 50. So I'm going to put a 50 on there. So let's find y at the moment that's all going on. So I'm going to have to run the Pythagorean theorem again. I'm going to have 50 squared plus 150 squared equals y squared. Now if I just take my calculator, I'm just going to punch that in. 50 squared plus 150 squared, 25,000. So 25,000 equals y squared. And then square root both sides to get your y. The square root of 25,000 is ugly. So I'm going to leave it because I don't want to round anything until the very last step. So I'm actually just going to leave it as the square root of 25,000. It's more accurate that way. Okay, so that's my y. So coming back here, for this y, I'm going to fill in the square root of 25,000 dy dt. And now I have everything filled in, and I can solve for dy dt. So 2 times 50 times 8 would be 800 equals 2 square root 25,000 dy dt. And then solving for dy dt, I can just divide both sides by 2 square root 25,000. Kind of ugly, that's okay, cross those out. So now you have dy dt equals, clear this, okay, alpha y equals, I've got, what do I have, covered it up, 800 divided by 2 times the square root of 25,000. And I'm getting 2.5298, so to thousands, I'm just going to round that to 2.53. 2.53 feet per second. That's going to be my final answer. And now I'm going to make my final statement. I've already written this out ahead of time to save time. And again, just pause the video to catch up. The final statement is, and I'm answering the question, I'm kind of restating the question again in my final answer and answering it. So the distance between the observer and the balloon is increasing at a rate of 2.53 feet per second when the balloon is 50 feet high. Okay, so we'll see you back for part 3, which will tackle the last example in the packet.